So, midterm exam, I think overall we did pretty well. Most of the scores were actually between 60 and 90, so I think that was quite good. Michael will discuss especially questions 1 and 2. They were not really problematic, so I don't think we need to discuss them here. If there are questions, Michael will do that on Thursday. The third one we discussed a little bit in detail. So that was just an accelerated point charge. It was given that you calculate the electric field of the point charge like that. And so the point charge is at the origin at 0, so the position is 0, and the acceleration goes to the z-axis, and it was given that you should express the results in terms of theta and phi going around this way. Okay, so velocity is 0, then of course our vector u is simply just c times r. R, of course, the r minus r prime is 0, this would be r w. That, of course, is simply just r, right? So u is simply just c unit vector. Then let's go from here. So this term then becomes easy. E squared cancels out. This is just c times r unit vector. What is this r dot u then? What is r dot u? That's this term. That is just r times this. So this is also just rc, right? So we have for the electric field already. So q over 4 pi epsilon naught. So here we have 1 over r squared c cubed, right? This is just r, this is r cubed c cubed. We're left here with c squared times u. U is just c times r, so this is c cubed r unit vector, right? And what is this thing here? Let's start from the right. It is u cross a here. U cross a. Well, u is just our unit vector. So u goes in this direction. It's r cross a. In which direction is that pointing? This vector cross this vector. Cross product points in what direction? Perpendicular to both of them, right? So it points actually into the board. Which unit vector is that? So this would be our r unit vector. The theta unit vector goes in this direction, right? What comes out of the board is the phi unit vector. Right? So this is just the length here is c, length is a, and so we said it points in the phi direction. Anything else that's missing here? What is the length of this? We have the length of u, the length of a. What's the length of the cross product? Length of the vectors times. What vector is missing here? C is the length of u, A is the length of A. The cross product has cosine. Cosine is the dot product. Right? Oh. So that's the sine, yeah? The sine theta. Sine theta. Okay, and now we do r, this is this r cross this thing, u cross A equals, so there comes in a length r. So we're now crossing something that's already perpendicular to r, cross r. So this cross r points where? Perpendicular to both, points in the theta direction. And they're already perpendicular, so there's no more sine theta term there. So it's just r c a sine theta, and then it goes in the theta negative direction. Okay. And that's what we have here. Plus R, C, A sine theta in the theta direction. So that is our electric field. Now, which term contributes to radiation here? And everybody wrote it correctly. You need to filter out the terms that only drop off as 1 over r, and everything else will drop to 0 to infinity. Which term goes as 1 over r? There's a 1 over r squared in front of everything. That's just a unit vector here. So that goes as 1 over r squared. So this we don't want. But here we have another length r, so that will end up being 1 over r, right? So we have our radiative electric field as q over 4 pi epsilon naught. And then we have 1 over r c cubed. There's still a 1 over c squared here, right? C squared, 1 over r, and here's a sine theta over r, and that goes in the theta direction. And that is our radiated electric field. And 1 over epsilon naught c squared, we can write as mu naught, right? Okay. So that's our radiated electric field. Right, mu naught q is. Okay. Then, how do you get the magnetic field from that? I think everybody had that correct as well. Magnetic fields as 1 over c pi unit vector cross E. And E. Okay, so we have R cross E. Now we're crossing R with something that goes in theta. What direction is that pointing? R cross theta. It goes back in the y direction. Just back out of the boat. And that only changes that, and we just have a factor of 1 over c from it, right? So that was q mu naught over 4 pi c a sine theta over r and going in the y direction, right? There, very good. Then, also everybody remembered how to calculate the pointing vector then. 1 over mu naught e cross e. That is, well, all the terms are essentially all the same. Just one of the mu naughts will cancel out, so that is mu naught over c q squared a squared over 16 pi squared sine squared theta over r squared. And in what direction is that pointing? E points in the theta direction, and D in the phi direction. The cross product of E cross B will go in what direction? And in any case, the radiation comes from the point charge. In which direction will the radiation propagate? That's what that tells you, right? In which direction is the energy flowing? So we have to look at theta cross phi. Where's that pointing?
The z direction.
Is that no?
Ah.
It's in our direction, right? You have your orthonormal basis, r theta phi, right? So theta cross phi goes in our direction. So that goes. So that goes in our direction. And of course that's what you expect, but anywhere you look, the radiation has to come right from the source, right? From the point source. Okay, so this is our pointing vector. And the last thing was then just calculate the total power. That is, well, integrate S dA over the surface of radius r. That goes cancels the r squared out. So mu naught over c q squared a squared over 60 y squared. And then we have 0 to 2 phi. And many of you keep calculating actually explicitly, so sine square theta, sine theta, d theta, and theta from 0 to pi. We can of course do that, but we've done that many times. The integral 0 to pi sine theta d theta, let's call x as cosine theta, and dx as minus sine theta d theta, right? Sine squared theta, so sine theta d theta, this would be a minus dx. Of course, we're going from cosine theta, so we're going from 1 to minus 1 essentially. So we can turn that around and go from minus 1 to 1 with a plus. Right? So x equals 1, x equals minus 1 here, right? Minus 1 to 1, dx, and sine squared theta is then 1 minus x squared, right? 1 minus cosine squared. So we have from this, nothing depends on phi, so we just have 2 pi. And we have the integral minus 1 to 1 minus x squared x, right? So this is equals 2 pi. And then we have x minus x 3 from minus 1 to 1, right? So that is 2 minus 2/3 here as 4/3. So this gives us 8. Right? So the total power is this times h pi over 3, so mu naught q squared a squared over 6. So that would have been the perfect solution to number 3. But you've probably seen I've been quite generous with partial brackets, as long as you've indicated somehow that you know how to calculate it in principle after more than once. Okay, any more questions on this? If there are questions on number 1 or 2, we shall do that on Thursday. What we should do is actually keep this here for later, so the radiative power for a single particle was mu naught a squared q squared over 6 c. This is something we might come back to later. Okay, so the general topic for today is now calculating radiation from any arbitrary charge and current distribution. So last time for the midterm, we're dealing with a very specific configuration, the dipole, an electromagnetic dipole. Today, we'll just keep that completely general. In that we have some kind of arbitrary source here. There's charge density prime T and current densities. At any point, we can call the center is here. There's some R prime within the source. And we're looking at that from some distant point away. Plus, we want to look at radiation, we want to look at something that goes up to infinity eventually. So the general assumption that we have is that we are much further away, so R being much larger than any size, any distance within the source. So our connection vector is in this thing here. This is our R. That's R minus R prime, right? Let's call this angle here, let's call it theta. So, first of all, general expression for the potentials. We will start with the potentials and calculate the fields from that, not use Jiffy-Nimbus equations because that actually gets messier than calculating the potentials. Now, potentials V of R and T in 1/4 pi not integral rho of prime time prime and the vector potential correspondingly with the current density. Okay. So this is of course the most general thing. Let's see what we can do to simplify and to figure out what of this could possibly make radiation and what the radiation fields will be. So first of all, let's calculate the length of this vector R. Right. That is, well, instead of cosines, this length squared plus this length squared minus 2 length times cosine theta. Right? So this is so R squared is R squared plus R prime squared minus 2R prime cosine theta. But R prime cosine theta is actually just the vector dot product here. Right? This thing is just R dot R prime. Right? So we know that R length is then just the square root of this, R squared plus R prime squared minus 2R prime. So the approximation that we'll make is that this R prime is much smaller than R. So if we want to take this to first order, we can already throw something out here, right? To first order in this again, the size of the source, which order R prime, there's already a second order term here that considerably neglect. That's a little small. So let's pull one R out of this here. Square root 1 minus, and we have to divide here by R squared. So this is our unit vector R prime over R. Right? So 1R comes out, which is the unit vector we divide by letter R. This is 1R. Right? Okay, what is the first order approximation here? First order Taylor expansion. It's R times square root of 1 minus something small. This is the first order. And 1 minus epsilon to the power n, the first order. 1 minus n epsilon, right? N is 1/2, so it's just half of this. So 1 minus R prime over R. First order. Okay? And then 1 over R to first order gives us, well, n will then be minus 1/2, and so it gives us 1 over R, 1 plus R, vector R, over R. Okay. Now, everybody remembers what the retarded time here is. T retarded plus T minus R over C. Now to first order, you can use this here as T minus R over C, and then plus, the R's will cancel out, R unit vector R dot X. Right? Let's call this thing here R naught, the retarded time to the center here, the center of the source. So we have retarded time as T naught plus some small perturbation R dot R prime over C. Right? That's what we have to use here for the time of the charge, right? So we then have rho of R prime TR, that is rho of R prime T naught, plus our small correction to our right vector R prime over C. Now we can do a Taylor expansion here as well, right? We can take rho, now we're expanding in length, we're expanding in time, right? First order, we can just take the time at this reference time, T naught. So it's rho of prime T naught. And then what will be the first order term if we account for this? So we now take an expansion in time, start out from our T naught, and then we go a little bit further in time. So the correction will be rho dot times this correction. So plus rho dot of R T naught times right? Okay. We have that. Let's plug that in. so our scalar potential R and T will then be, so 1 over 4 pi epsilon naught. We're integrating rho pi. So first we have the rho. For rho we say r prime T naught plus r prime over C rho dot r prime T naught. That is our first approximation. Over, and then we use the 1 over r right here. So 1 over distance to the center of the source times 1 plus r unit vector r over r. Right, and that whole thing we integrate into r prime. Okay. One thing we can already throw out now. See, we have the 1 over r. In fact, we didn't really have to do that approximation because we have a 1 over r here. There's no length r, there's only small r prime, size of the source. And then we get another 1 over r in here. So whatever comes out of this term will drop towards the potential that's already as 1 over r squared. So we know already that's not going to contribute to radiation. Right? So we can already drop this one here. So we really have to do only the 1 over r terms. Alright, so that means in that approximation we have one term here that involves effectively rho of r prime T naught d3 r prime. What is that? So everything else depends only on our coordinates, not anything in the source. So really the integral integrates over rho. What is that? Charge density integrated over the whole volume. What does that give you? The total charge, right? That is your total charge. Good. Then we have a second term here, where we're multiplying with r dot, we can pull that out. The actual integral is something like r prime rho dot of r prime T naught and d3 r prime. But see now, the only thing that's time dependent here is of course rho. So we can just as well write the time derivative in front of the whole integral. Right? Integrate the whole thing. I mean, we're integrating over all r, nothing depends on time, only rho. So this really is the integral of rho dot. But what is this thing here? That's the charge times displacement integrated over your volume. What is charge times displacement? We had that in the dipoles, right? Charge times length of the dipole was the dipole moment, right? That's the definition. So this is our dipole moment P of T. So what we have here is we have 1 over 4 pi epsilon naught. Then one term that is just charge over r. And the second term, that is, now we have to pull this r prime out here. This r unit vector out, this r unit vector dot p dot over r. Right? That's the only terms that could possibly contribute to radiation. Okay. Shall we look at the vector potential A here? See, this is difficult to read as well, right? Green work better. A, yeah. Okay, let's look at what we can do there. 4 pi. We're integrating. Because if we integrate over the charge displacement, the charge current density, J, the current density of R prime TR over R prime. But what this really is, this is integrating the motions of charges throughout. This is essentially something like rho times velocity, times change of displacement. Right? If we have integral J d3 r prime, that actually is nothing else but the change, that's the time derivative here, change of displacement of the charges over time. That's current density. So this really, again, is our P dot. But that effectively already has the length r prime, something size of the source, in it. So this is already first order in our approximation that we take only first order in r prime. So for the purpose of radiation, we can very simply just write this at our time T naught. So this is our P of T naught. Okay, those are our potentials. Almost everybody remembered in the midterm exam how to calculate the fields from that, right? Calculating the fields here, electric field equals minus gradient V minus A over T equals gradient V. So it's minus 1 over Q. Let's write this out. Gradient of V is 1 over 4 pi epsilon naught. This, of course, gives us just minus Q over R squared unit vector, right? That's the 1 over R term. And then gradient of this, we take the gradient with respect to R here. Then there's another term here, R dot P dot over R squared. Our unit vector, right? That's the 1 over R from here. And then we have a gradient from the P dot here. So the P dot is evaluated at T naught. T naught was T minus